Okay, so 1.1, state the type of this differential equation. Like I said, for 1.3 it says find the integrating factor, so that gives you a clue. It's a linear differential equation, or first order linear differential equation. Yeah, let's put differential equation. Okay, so a lot of students just wrote first order. Okay, that's not enough. It needs to be first order linear, because all of the ones that we've looked at were first order, right? There was always y prime. We never ever looked at y double prime or triple prime or anything. Okay, so first order, that's partly correct. You need to say also that it's linear. Okay, 1.2, rewrite this in standard form. So that's, we need to divide through, there we go. We need to divide through by the x so that the coefficient of y prime is just 1. And then that gives us what everything should be. So dividing through by x, we get y prime minus 1 over x times y is equal to sine x. Okay, as long as you have the coefficient of y prime being 1, then that's fine the way it is. Okay, then anything else with y, we leave it on that left-hand side. Everything else we put onto the right-hand side. But there's only one term there, so we leave it as is. Which means this first bit here, that's going to be our p, and that is our q. Okay, so p and q. Okay, so that was the 3 marks for that. Rewriting it, and then p, and then q, the 3 marks. Okay, determine the integrating factor. So we got our p, 1.3. So mu is equal to e to the integral p of x dx. It's out of 2. I gave 1 mark if you knew what to start with. If you made a small mistake later on, that was fine. So you got the 1 mark if you knew where to start. Okay, so this would be e to the integral minus 1 over x dx. A lot of students left out the minus 1 there. So you had p is minus 1 over x, and then you left out the minus there. Okay, so please make sure that if your p is minus 1 over x, then you put the minus there as well. So this is going to be e to the minus log x, so that will be 1 over x. Okay, so you can take the minus inside the log to make it 1 over x, then the e and the log cancel, so we just left with the 1 over x. Okay, so that was the 2 marks for that. Okay, write out the solution without attempting to solve the integral. So we write it out in that general form. So y is 1 over mu integral mu q dx. That's all you need to do. Okay, it's just that integral there. Then the mu, that is 1 over x. So 1 over mu is going to be x. And then q, that was sine, so we had sine x over x dx. Okay, so you just had to write that out. Okay, so that was 1.4. 1.5, what do you notice about the integral? This is the sinc function. Okay, that's the one that we were looking at. I'll put it at the top of the page. Okay, next, briefly explain why this would be difficult. If you said anything at all about integration by parts or U substitution or whatever method that you've learned previously that you could use, I gave you the marks for that. Okay, so if you said if you do U substitution with the 1 over x and you get something difficult, or you try, you can't do a trig integral, remember those are the special forms for that. But if you said something about a trig function, dividing by x, that's complicated, or integration by parts will be complicated. If you mentioned any technique whatsoever, I gave you the marks for that. If you just said it's difficult or I don't know how to do it, I can't give you marks for that. Okay, if you mentioned any technique at all, I gave you the marks. Okay. Any questions about this so far? No questions. Okay, next part. Okay, let's try and make this a bit bigger. Can you see that in the back? Is that fine? Okay, so question 2, this was on the Taylor series part. So we've got the sinc function, and then if you follow these 3 steps, you get the approximation. So number 1, determine the Taylor series. So we know that sine x is given by the sum k equals 0 to infinity minus 1 to the k over 2k plus 1 factorial x to the 2k plus 1. We did that, I think, once in the tutorial. There was something like this, and then we did this a couple times in class with the sine function, and then we did a similar thing with the cos function. So you should know what they are by now. But that sine x, we wanted the sinc x, so we need to divide by x. So sinc x. Okay. A lot of students wrote sinc x without the c, okay, but then they wrote sine x over x. I ignored that. Okay, so remember it's S-I-N-C. Okay, some students left that out, but I ignored that. So this was sine x over x. So we're dividing by x, so on that right-hand side we divide by x. So each term we divide by x. Okay, so that x to the 2k plus 1 becomes x to the 2k. Okay, so this will be k equals 0 to infinity minus 1 to the k over 2k plus 1 factorial x to the 2k, because that extra 1 from the x to the 2k plus 1, that goes away when we divide. Okay, is anybody not seeing that? Is that fine? Okay, so that's it for 2.1. 2.2, write out the first 4 terms. Okay, so all we do is we look at k equals 0, 1, 2, and 3. So we don't go up to k equals 4 because we're starting counting from 0. So it'll be 0, 1, 2, 3, that'll be 4 terms. Okay, so when k is 0, minus 1 to the 0, that's just 1. The bottom part, 1 factorial, that's 1. X to the 0, that's 1. Everything's 1. Okay, next one, when k equals 1, the minus 1 to the 1 will now be a minus. So it will be 1 over, and then if k is 1, we get 3 factorial. X to the 2. Plus, and then that just continues with those odd numbers there. So we have 1, then 3, then the next one will be 5. So 1 over 5 factorial x to the 4 minus 1 over 7 factorial x to the 6. Okay, so you just had to write that out like that. Okay, so a lot of you put that in your calculators to see what the exact value is. That's fine, but you can leave it like this. This is no problem with that. Okay, that's a 5 factorial. So this is the first 4 terms from that sum on the right there. Okay, so that was 2.2. 2.3, find the solution using this approximation of the sinc function. So everything here is approximately the sinc function, right? So if we have all the terms, then it's equal to the sinc function. If we only have some of the terms, then it's approximately the sinc function. Okay, so we did that with the Taylor series. If you stop at a certain point, it's just an approximation. Okay, so all we do is we take that polynomial and we put it in that integral we had before, this one over here. Where I wrote sinc, we put in those 4 terms. Okay, so y equals x, the integral sinc of x dx, and then we can put our polynomial in there. Okay, so this will be x integral of 1, and then alternates minus plus minus plus, so it will be minus 1 over 3 factorial x squared plus 1 over 5 factorial x to the 4 minus 1 over 7 factorial x to the 6. Okay, so all of this. And then you don't need to put the plus c now. You can put it once you're done with the integral. But we know for the indefinite integral, we're always going to have the plus c. So I just put it there so we don't forget it for later. Okay, so this is going to be, we can separate this out. So it will be x integral 1 minus 1 over 3 factorial x squared plus 1 over 5 factorial x to the 4 minus 1 over 7 factorial x to the 6. and then plus cx. So I've just taken the x and put it at the end there. Okay, now we can integrate just using the power rule. So x squared, we add 1 to the exponent to make it 3 and divide. X to the 4, add 1 to the exponent to make it 5 and divide, and so on. So it will be x into, that will just be an x, minus 1 over 3 times 3 factorial x cubed, plus 1 over 5 times 5 factorial x to the 5, minus 1 over 7 times 7 factorial x to the 7, plus cx. Again, don't forget your c when you've done your integral. So you can put it right away like I did, or you can put it at the end, but make sure you do have that. Okay, finally, we can write everything out by multiplying that x out in front. Okay, if you didn't multiply the x, I still gave you the mark, but if you want to write it out individually, you can. So it will be cx plus x squared minus 1 over 3 times 3 factorial x to the 4 plus 1 over 5 times 5 factorial x to the 6. So I'm just adding 1 to each of the exponents. Minus 1 over 7 times 7 factorial x to the 8. Okay, so once you substitute your polynomial, you integrate. Okay, you've done all of that before, integrating a polynomial. And then a lot of students left it here, this x times the bracket. That's fine, everything was correct for that. But if you did multiply it out like that, that's fine as well. Okay, any questions on this? Okay, so everyone's fine with integrating the polynomial. Okay, last one. Okay, so we've made this approximation. Now we want to see, does it actually work? Can we use this approximation? So we know that with Taylor series, sometimes the interval of convergence is minus infinity to plus infinity. So we showed that in the lectures with the trig functions, the exponential function, and then we did one with cos x over x, I think one of the later lectures, and we showed that those converge for all x values. Now here we've got sine x over x. Maybe it doesn't converge for all x values, so we need to test it. Okay, so 3.1, we need to see for which values of x does it converge. So how do we show if it converges or not? We use the ratio test. Okay, remember the ratio test. That was the limit n goes to infinity, an plus 1 over an, and we want this to be less than 1. If it's less than 1, it converges. If it's bigger than 1, it diverges. If it's equal to 1, then it's inconclusive. We need to try something else. Okay, so that's for general series. But when we're working with the Taylor series specifically, we always use the ratio test. We don't use anything else. Okay, so if it's specifically convergence of a Taylor series, you always use the ratio test. If it's a different series, okay, like we had in the previous chapter, then you can use the ratio test, you can use the alternating series test, integral test. Remember, there was that long list. Okay. But Taylor series, we specifically use this one every time. Okay, so let's see what we get. So we have the limits. N goes to infinity. An plus 1. So we look back at the Taylor series. Wherever we have an n or a k or whatever we use, we now put n plus 1 or k plus 1. So let's just write that on the side. So remember, we had the sum. N goes from 0 to infinity. Minus 1 to the n over 2n plus 1 factorial x to the 2n. So now we look at a specific one, so just n, one of them. Then wherever we see an n, we put an n plus 1. That's for our an plus 1. So it's going to be minus 1 to the n plus 1. And then we've got x to the 2n, but if I replace n with n plus 1, it becomes 2 times, and then in brackets, n plus 1, so it'll be 2n plus 2. Okay. Again, if you factor out the 2, you end up with 2 times n plus 1, which is what we wanted. Okay, divided by 2n plus 1, and again, we replace the n with n plus 1. So it's going to become 2n plus 2 plus another 1, so it will be 2n plus 3. And then the factorial. A lot of students did get to this point, but then just crossed out the factorial at the top and the bottom. Okay, you can't do that. You can't just cancel factorials like that. We need to simplify it first, and then you can cancel. Okay, so I'll show you what I mean now. Okay, so that's an plus 1. Then we're dividing by an or multiplying by the reciprocal. So we can just swap the term around. So the 2n plus 1 factorial goes to the top. The minus 1 to the n and the x to the 2n now go to the bottom. Okay, or you can write it as a fraction divided by another fraction. That's fine as well. But when you simplify, you'll end up with something like this. Okay, now here we want to cancel these factorials. Here we've got 2n plus 1 factorial. Here we've got 2n plus 3. So they're close, but we can't just cancel them. We need to do a bit more work. But for now, we've got this minus 1 to the n plus 1 and the minus 1 to the n. Notice how everything is in absolute values. So if it's negative, it goes away. So that goes away. All of that bit goes away there. And that goes away there. Okay, so we're left with the limit, n goes to infinity, x to the 2n times x squared. I'm going to separate it out because the x to the 2n from the top can cancel with the x to the 2n at the bottom. And then I still have the 2n plus 1 factorial. Okay, 2n plus 3 factorial. Remember how factorials work? If I have 5 factorial, it's 5 times 4 times 3 times 2 times 1. So 2n plus 3 factorial will be 2n plus 3. The one before that will be 2n plus 2. And the one before that will be 2n plus 1, which is what we have at the top. So we can stop there. Factorial. Okay, and then we have x to the 2n left. Okay, now we can do a bit more cancelling. We have an x to the 2n at the top, x to the 2n at the bottom. They can go. 2n plus 1 factorial at the top, 2n plus 1 factorial at the bottom. They can go. And lastly, x squared. That has nothing to do with n. Okay, there's no n involved, so we can take that outside of the limit. So this will be absolute value x squared, or you can drop the absolute value since we know it's positive, or you can leave it there. That's fine. Okay, then we have the limit, n goes to infinity, 1 over, and then the bottom part, you can multiply it out, or you can leave it as is. That's fine. Okay, now we can take the limit. The top is just 1, that doesn't change. But the bottom part, if we multiply it out, we'll end up with something n squared, right? If we just multiply it out. Now, when n goes to infinity, n squared will also go to infinity. So that means the bottom goes to infinity. If the bottom goes to infinity, the whole thing goes to 0. So all of this goes to 0. Okay, you can multiply it out and show more steps. But if you just said it goes to 0, you got all the marks. Okay, so I'm not worried about all the steps in between. We know it goes to 0, you can just write it like that. So 0 times x squared, that's just 0. Now, what did we want? Let's go to the top. We wanted the limit of that stuff to be less than 1. Here we got 0. 0 is always less than 1, so it always converges. Okay, since it always converges, you can just say it always converges, that's fine. Or you can say the possible x values lie between minus infinity and infinity. So you can say minus infinity less than x less than infinity, or you can write it like this. Or you can just say any real number. Okay, I'm not too worried about how you write it, anything like that's fine. Okay, so we know it converges for any x value. That's proved. We know that now. If we go here, 3.2, given your answer to the previous question, would the approximation be valid on the interval -1 to 1? Well, we just showed it works for any x value. If it works for any x value, it has to work for these x values. So, again, I didn't worry too much about what you wrote. So since x can be any value, it converges on -1, 1. Or something like that. If you said -1 to 1 was a subset of the real numbers, or anything like this really, I gave you the marks for that. Okay, but you have to have some reason. You can't just say it converges. You need to say why. Well, why does it converge on this interval here? Okay, and that was everything. Okay, any questions on this part? You're good. Okay, no issues with this. Okay, we're not going to go through this again, so this is your last chance to ask. Okay, so that will be it for Taylor series. So we're done with this chapter now. The next thing that we're going to be going through is complex numbers. So I did upload 2 videos already. That will be the introduction to complex numbers. So next week we will start it properly with applications of complex numbers. We'll look at what we can do with them. And then the last thing we will do is integration with complex numbers. Okay, so we'll see that those integrals that you looked at in the first semester, those really difficult ones, they end up becoming really easy once we use complex numbers. Okay, so that will be the last thing that we look at for the semester.